It's Mr. Gritto again. So this lecture is supposed to go along with lecture 3 of your notes. So we're going to be talking about 2 out of 4 of the trends you will eventually learn for the periodic table. We're going to talk about how the periodic table helps you learn atomic radius and how it helps you figure out ionization energy. How you can compare those two things with elements on the periodic table just by their location. Alright, so you guys should have the guided notes for lecture 3. You can find it on the staff webpage under chemistry. We want to talk about ionization energy and atomic radius and kind of what accounts for those differences in elements. Why are some bigger than others? Bam. Alright, so first up. No, you can also follow along section 6.3, page 170 of your textbook. First up is atomic radius, which if you think of radius, you should kind of imagine like circles, things like that. It's basically how big an atom is, right? So atomic radius is telling you how large or small an atom is. Well, it's kind of weird because if you think the electron cloud model, the quantum mechanical model, it's kind of hard to describe the boundary of an atom. Atoms are fuzzy, atoms are weird, right? So the way they've come up with one of the conventions for atomic radius, the way they do it is, let's look at this example down here, atomic radius of hydrogen, H2. So two hydrogens bond together. The way they figure out atomic radius is they bond the element together with itself. So here we have two hydrogens bonded together. And to figure out what the atomic radius is, to find that atomic radius, they take the distance from the two centers and they cut in half, which in theory should give them the radius of that element then. Right? They technically could use this distance as the diameter of the element, but they do it this way to define the atomic radius of an element. And that's where they get these numbers from. Typically you'll see them with other two units. You'll see PM, which is picometers, and that A with a little 0 at the top, angstroms. Like a picometer, I think is 10 to the negative 9th meters, like very, very tiny, right? Which atoms are extremely tiny, so it makes sense. So if we use this element as an example, we could see that the total distance between the two nuclei, nuclei, is at 266 picometers. The atomic radius, therefore, is half that, which 266 divided by 2 is 133 per picometers. So that's the general definition of atomic radius. Why this kind of gets important is, if you think about computer chips, you know, carbon and silicon are in the same group. They're both in that group 14. Which one would be better for computer chips if we want to make a computer like really, really tiny? Whichever one has the better atomic radius, or the smaller atomic radius, would end up being the better choice of an element for a small computer and things like that. So atomic radius doesn't come into play because it'll make elements less clunky. Right? So here we can see sodium's atomic radius and chlorine's atomic radius and them bonded together. One thing to note, ions are going to change their size. So here sodium's nice and big, but when it bonds, when it has a positive charge, it gets smaller, where chlorine gets bigger with that negative charge. That's something we'll look at farther down the line. But no, the size of the atoms will determine how they can bond because of basically space. You can only bond so much if you're so tiny or so big. So let's focus on trends in atomic radius. Here's our periodic table with somewhat accurate atomic radii for all your elements. You can see the numbers here corresponding them, so you can correspond rows and columns. So there's two trends that you kind of want to see. What happens when you go down a group, so where groups are similar properties, and what happens when you go across a period, our horizontal rows. And you also kind of want to think about why this stuff is happening. What might account for these changes. Alright, so let's focus on going down a group. Just looking at our first group, the alkali metals, we can see that in general, it looks like as we go down, the atomic radius is definitely increasing. 1.28, 1.66, 2.4, 2.60. Alright, if I look around here, it looks like francium is definitely the biggest guy also. That's kind of cool. Biggest element is francium. Woohoo. Alright, so as you go down, your elements are getting bigger. Your other general trend as you go across a period, it looks like the elements are getting smaller. There are some exceptions. There's always exceptions to the rule, so here's an exception, 1.2, 1.19, but in general it seems to be getting smaller as you go across. Now that one's weird. We'll talk about that soon. So, first pattern, going down, why is it getting bigger? If you think about it, it kind of makes sense because every time you go down a period, every time you're going down this group, right, you're adding an energy level. And that's what's going to be one of the main things that causes these elements to get bigger. Every energy level you add has all those inner energy levels kind of shielding it from the nucleus. So what's really accounting for the size of atoms is the pull from the protons pulling on the electrons. Here, because you're adding energy levels and you're adding more electrons every time, the atoms are getting bigger because those electrons on the inside are shielding them from the outside, and also because of that added energy level. So two reasons it gets bigger as you go down: electron shielding. So electrons are shielding the outer electrons, allowing them to get farther and farther away from the protons. And also that added energy level is going to make it a little bit bigger. Now if you remember, a period is all the same energy level. So for fourth down here, the outermost energy level is the fourth energy level. As we go across, our elements get heavier, they add more protons, they add more electrons, but the really weird thing, they actually get smaller. And the way I like to think about it, and the way it's described is, imagine like a really strong magnet. The stronger a magnet becomes, the easier it is to pull things in towards it, right? And that's what's going to explain what's happening here as it goes across. I told you guys you're adding protons, electrons, mass, all those things. The key idea with this is that additional protons you add as you go across. So cobalt with 27, krypton with 36. That those additional protons are going to pull the electrons, that outermost energy level, closer and closer. That pull from the protons in the center, that stronger pull, is known as a stronger nuclear charge because it's the nucleus that's pulling them in. Stronger nuclear charge. So our two trends are increasing going down, decreasing going across, and it's energy levels and electron shielding, and then nuclear charge for across. What's accounting for those changes? If we look at our table, some other good things to know are francium is your smallest guy. Francium is your biggest element, and helium up here, the very top right element, is your smallest element. So in general, you could say your trend looks like a diagonal arrow heading towards francium. The reason this comes into play is if we want to order elements from largest to smallest, we could easily use the periodic table to do that. So let's do this first column together. So lithium, francium, and potassium. If we look at our periodic table, here they are: lithium, francium, and potassium. If we want to place them in order of increasing atomic radius, all we have to do is go straight down that line. Lithium is going to be bigger or smaller than potassium. Potassium is then smaller than francium. So our answer ends up being LiKFr. And you do the same thing for these guys based on that same trend. Alright, the next topic we want to talk about is ionization energy. And what ionization energy is talking about is it's the energy to remove an electron. So there's going to be more than one ionization energy. To remove the first electron, it's known as first ionization energy, and that's the trend we're going to look at now. So first ionization energy, energy required to remove an electron. Here's our table. So energy is measured in kilojoules per mole. So per mole of the substance, how much energy does it take to remove all those electrons? Here's our data table, a scatter plot of our ionization energies. I usually have my students take a minute to take a look and see if they can see any patterns in here. So think about that for a second. Do you see anything common between the normal periodic table and what's going on with this guy, this data plot, scatter plot. Some things you might start to notice if you're looking at the periodic table in this is look at all the peaks. There's helium, there's neon, argon, krypton, xenon, radon over here. All those peaks correspond to elements in the same group. The noble gases we talked about as being the most stable elements around. So all your peaks are part of your noble gas group. The rest of them are based on the columns, and as you go across the column, you'll kind of see a general trend. Remember, all trends are broken, all trends have little weird dips and things like that, but as your atomic number increases, as you go across a group, so period number 2, as you go across a period, horizontal row, if you look at the second period, you have lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine all in the same row, in that order. As you go in that order, it looks like the ionization energy is increasing. Now, let's take a look at our periodic table. So, we saw the highest ionization energy is helium. So this guy's our biggest thing. Looks like our lowest is down here with like radium, but it only goes up to atomic number 86. Our lowest ionization energy is actually going to be francium. So it looks like as you go up the periodic table, your ionization energy, the energy you need to remove an electron, increases. It takes more and more energy to take an electron as you go up the periodic table. As you go across, it has that same exact trend. As you go across, it requires more and more energy to remove an electron. Now, if you kind of compare this to atomic radius, there's something weird going on. So atomic radius, we look back, increases going down. Ionization energy increases going up, exact opposite. Atomic radius decreases as you go across. Ionization energy increases as you go across. And there actually is a reason for that direct correlation. The smaller your element, so helium's extremely tiny, the harder it's going to be to pluck an electron away from it. That's because if the closer you are to the protons, the nucleus, the stronger the protons have a pull on you. If you're close, you're being influenced by those protons a lot. So the closer you are to the nucleus, the stronger the ionization energy. So in essence, the smaller the atom, the stronger the ionization energy. What's going to be cool, remember how we put these guys in order from in smallest to largest before? Where it's like lithium, potassium, francium. The ionization energy from smallest to largest is going to be the exact opposite. Right, so in this case, it would be francium, potassium, lithium. So the exact opposite, which is kind of cool. Alright, so those are your general trends for ionization energy and atomic radius. Give some practice to these problems. Try to figure out what the order are. I do give some tricky ones where I give you diagonals instead of just straight up and downs, or I give you L shapes or corners. It's fun to try to figure out which one's has the biggest atom, which one's the smallest atom, which one requires a lot of energy, which one doesn't require much energy at all. Alright, so those are the first two trends we'll talk about in the periodic table. Good luck. Dun dun dun. Where's the dun, darn it?